Hello everyone, my name is Guy Tenenholtz. Today we will talk about offline reinforcement learning. This tutorial will start with a short introduction of online reinforcement learning, after which we will talk about the difficulties in offline RL and go forward into showing some practical algorithms for offline reinforcement learning. So let's begin. Before we can start, again, it'll be good to give a short recap on online reinforcement learning. As probably most of you know, reinforcement learning has become something very strong in recent years, a very strong tool that has proven itself to solve very difficult problems. We saw DeepMind mastering the game of Go, after which we saw other great successes from mastering games like StarCraft 2, Dota 2, the Atari suit. We saw many different complex robotic manipulation tasks, things in medicine, and so on and so forth. So an online reinforcement learning consists of an environment. Right, this environment could be, for example, a chess game, and an agent interacting with this environment. So the agent in this example of a chess game might be one of the players playing in the game. So the agent can take an action in the environment, and the environment is affected by this action by transitioning from a state that it's currently at to another state, according to the action that was taken. Okay, based on a transition probability kernel that tells it the probability of what state it can transition to, given that it's at a current state. Now, the feedback of the environment to the agent is given by a reward signal and some kind of observation. And the agent receives this reward and observation and decides again what it can do according to what it's seen so far, takes another action, and again the environment transitions its state, gives the agent a feedback of reward and observation, and so on and so forth. And the agent keeps interacting with the environment in this manner. Now, the most general framework that is used in reinforcement learning is the partially observable Markov decision process, POMDP. And so this framework consists of a state space, S, an observation space, O, and an action space, A, where the state space, for example, in our example for the chess game, could be maybe the state of the actual board, right, where every piece on the board is. An observation space could be something that is related to the state space, giving us information of the state space. So in the example of the chess game, it might be a camera looking from a third view perspective on the board, giving us some information on the state. And an action in this example would be things that we can do in the environment, for example, moving pieces on the board. Other things that we have in POMDP is a reward signal. It's a scalar function that for every state in action would give us a number telling us how good it is to be in that state or action. And finally, we have a transition function, an observation function telling us what the probability of transitioning between states are, and what are the probabilities of seeing observations given that we're in a state. And of course, we do not necessarily know these functions. So maybe in a chess game we would know these functions, but in general environments there's no reason to believe we know the transition function or observation function. It's something we might want to in some way learn on our own. And the difference between POMDPs and MDPs is that MDPs would not be partially observable, meaning the state space would equal the observation space. Okay, so in most cases we'll discuss MDPs in reinforcement learning. In offline reinforcement learning, when thinking of POMDPs, of partially observable Markov decision processes, the problems become much harder than what we're used to in online reinforcement learning, and I'll touch this aspect a little bit later. I'll I'll explain its relation also to causal inference. So it's a pretty important aspect in offline reinforcement learning. What else do we have in reinforcement learning? I told you how the environment works, what the basic framework is. What else do we have? We have the agent. The agent is a policy. It gets to see all the histories of all the observations and actions and rewards it saw so far and decide on an action based on all this information. Many times the agent can also choose to be stationary and only decide on an action based on the current state that it's at. But in general, an agent, a policy, could depend on its full history. Now, other than the agent, we have our value. This is a very important function. That this is actually the function that we will want to maximize later, telling us how many rewards we got so far. So given a policy pi, the value of pi at state S is the sum of rewards, discounted rewards, starting at that state S. Now, the discount factor gamma here controls how much weight we want to give to to rewards that are near in the future than rewards that are farther away from the future. So we can choose any number between 0 and 1. If gamma is less than 1, then the horizon h here can go to infinity. So we could look at the sum, the cumulative reward, discounted reward from now till infinity, and that would also converge. So that would be the value of our policy. The expected sum of rewards would be the value of our policy. And again, this is something we're going to try to maximize in reinforcement learning. Other than the value, we also have another very important function which is related to the value. It's known as the Q function. The Q function, unlike the value, lets us choose to do a different action at state S. So the Q value of SA of policy pi is the expected sum of rewards, only that at time 0, when we're at state S, we get to take action A. And after taking action A, we follow policy pi. So that's the difference between the value and the Q function. The value looks at the expected sum of rewards over policy pi, and the Q function first takes an action A based on the input to the function, and then follows policy pi. And like I said, the goal of reinforcement learning is to maximize a value, find the policy, the best policy, the policy that would get the maximum expected sum of discounted rewards. Now, like I said, the value and the Q function are very important functions in reinforcement learning, very useful. And they're also related, of course. It's pretty intuitive to see that they're related, and actually the value and the Q function are related in this way. It's the expectation over the action, given that the expectation is induced by the policy pi. So that is the relation between the value and the Q function. And even more importantly are the Bellman equations, which relate the Q function to itself. So basically the Q function, we can write the Bellman operator, which is denoted here by this script B. So the Bellman operator is given by the reward plus gamma, the expected value of the next state. Okay, so this is how the Q function and the value of the next state are related. And of course, the expected value of the next state can be written in terms of the Q function. So in this way, we can relate the Q function to itself using the next state, expected value of the next state. And this is very important because it allows us to learn a Q function, right? So here's an example. This is a general actor-critic framework. We assume some parametric critic, Q of theta, and parametric policy, also known as an actor, pi of phi. And these could be, for example, neural networks. And actor critic works in two steps. First, given that we have some policy pi, we try to learn the Q function of this pi, and the way we do this is using the Bellman relation, right? So we try to solve this regression problem in the first step, where we try to fit the Q function to its Bellman counterpart, right? So the Q equals R plus gamma, the expected value of the next state, which we can write it as the expected Q function over the next action. So we could learn the Q function of policy pi that way, and then in the second step, we would take in a way a greedy action with respect to our current Q. So we'll try to maximize the policy over the current Q function, thereby increasing the value of the current Q function, and then return to step 1 to learn the Q function of our current policy, and so on and so forth until this algorithm would converge to an optimal policy. So this is like a general actor-critic framework that we'll return to later in our offline setup that can learn an optimal policy. Now, what we want to do in this tutorial, we want to talk about offline reinforcement learning. We want to talk about reinforcement learning when only offline data is available to us. Now, how is this data going to be generated? So let's see. We need some more notations here. So we have say the environment initiated at some sampled state S0 that was sampled from some initial distribution. And then the way the data is going to be generated is by some policy that we're going to call the behavior policy, which we don't necessarily know. But this behavior policy chooses an action A0 at that state. Okay, we don't know why it chose action A0 and what the actual function this policy uses, but it chose an action A0. After choosing action A0, we get to see a reward R0, and the environment transitions to state S1, after which the behavior policy takes an action A1. Again, we will receive a reward, transition to the next state, the behavior policy will take another action, and we'll receive a reward. Now we assume that we're getting data where we get to see this S0, A0, R0, S1, and so on and so forth. So these tuples of S, A, R, S prime of the next state, we see these trajectories of what the behavioral policy did and what it saw. So we're going to be getting these trajectories from the behavior policy. So this is one trajectory. We could see another one, maybe the trajectories would intersect in certain states even. And we're going to get all these trajectories, which eventually will construct us a data set of trajectories or transitions that the behavioral policy made. And now we want to use this data in order to learn perhaps a better policy that is in this data in some way, but without interacting with the world. So before we continue, let's try to understand why do we want to use offline data in reinforcement learning. Now, in general, like you see in the diagram here, offline data can be used together with an environment. Okay, so we could interact with the world while also utilizing data. And by why would we want this data? First of all, we already have a lot of data in a lot of different domains. More importantly, online interactions in many settings is something that could be very costly. If you think about maybe training an autonomous vehicle, then buying a fleet of cars and taking the time to send them out to drive around is something that will cost us a lot of time and money. Other than that, it's very unsafe, right? To train a car, an autonomous vehicle in the real world where real people, real pedestrians are walking, could actually kill someone, right? An even more important domain might be in the medical domain, where we want to administer certain treatments to patients, and I'm guessing we wouldn't want to start administering random treatments to patients if we don't really know what they do. And we might want to first utilize some data to understand what happened in the past before we try to attempt something on our own. Some random autonomous agent might do things that are very unsafe. Other than that, offline data many times contains expert behavior, right? If we see a doctor treating patients, then this dog probably has a lot of knowledge, and he or she knows what to do. And using such data, using such expert knowledge, we can actually start off from not from scratch. We can start from pretty good policy, which we could then improve upon the expert data that we have. And sometimes the data is not fully expert, and we can really improve upon it. But still, it's somewhere to start with. So using data can bring us this great starting point and warm us up. And like I said, offline data is already available in many different domains, from games, healthcare, autonomous driving, education, and so on. And here, what we want to do is solely learn from offline data. So we're not going to be using the environment at all. Of course, that in the real world, we would have this process of interaction with the world, collection of new data, perhaps asking for new data from experts. But in this scenario, we're only interested in the pure offline setting and asking questions of what can we do when we're given offline data and do not have the ability to keep interacting with the environment. What can we do in this setting? All right, so before we continue talking about offline reinforcement learning and getting into the actual details, I want to talk about the vast amount of related literature that we have to offline reinforcement learning. So first of all, we have off-policy evaluation. This is a field with an enormous amount of research and works that people have done. And it deals with the same setting in which we have a behavioral policy that generated some data for us. And the difference is that in off-policy evaluation, what we're trying to do is find the value of some given policy, given that we're given this data of a different policy. And it turns out that this is a pretty hard problem. And even today, while there are a lot of different methods and very many bias and variance trade-offs that people have found, it still is an open challenge and a very important one to be able to do such a thing. Other than off-policy evaluation, we have off-policy reinforcement learning. Now, the main difference between off-policy reinforcement learning and offline reinforcement learning is that usually off-policy reinforcement learning considers off-policy algorithms such as Q-learning. But it's many times when people talk about off-policy reinforcement learning, they do not assume that we can't continue collecting data. So when I say off-policy reinforcement learning, I'm talking about algorithms that can work off policy, that can use data that was generated by a different policy, maybe an old policy that the algorithm itself generated earlier, like in Q-learning. But these algorithms usually keep collecting data on their own. So they're using off-policy data, but they're still collecting and exploring the world. In offline reinforcement learning, we're not going to allow that. Okay, so in offline reinforcement learning, we have some fixed data set that was generated by some unknown policy. We cannot keep interacting with the world, and we want to do the best we can with this offline data. Obviously, we can't even really converge to an optimal policy because we might not even see the full state space. Okay, but we want to do the best that we can with the data that we have. Okay, other than these two, we have imitation learning. Imitation learning deals with offline data when we know that or assume that the data contains expert behavior. So the behavioral policy that generated the data was the optimal policy. And in this scenario, we don't really need to try to do any reinforcement learning or improve the policy. All we have to do is try to imitate the data that we have. So things like behavioral cloning, which are much easier to do as we provide them a ground truth signal to be able to run supervised learning algorithms. So these problems are usually much easier than reinforcement learning, and they allow us to mimic the data. And also, of course, a vast array of research here. And lastly, I want to touch a field that might not seem exactly related to offline reinforcement learning, but in fact, it's very much related to offline reinforcement learning. And that's the field of causal inference. And how is causal inference related to offline reinforcement learning? There's a great tutorial, by the way, by Elias Berenboim about causal inference and reinforcement learning that I really suggest anyone who's interested to consider looking at. My perspective of causal inference and reinforcement learning is that when we want to do or somehow do reinforcement learning on offline data, but this data is partially observable. Recall that partial observability means that we don't see the full state, but perhaps the behavioral policy that generated the data did see parts of that state. And when that happens, when we don't see the state that the behavioral policy saw, and we got data, we only get observations of that state, then those states, which we don't know of, are known as unobserved confounders in the causal inference literature. And then when we try to do reinforcement learning, we're actually asking counterfactual questions under hidden confounding. And this is, again, a vast array of research in causal inference. We're not even promised that we're able to do this. Maybe the problem is not even identifiable. So it's important to understand that when we have partial observability, then things become much more difficult, especially when we're dealing with offline data. And partial observability is probably something that is always inherent in every problem that we're going to be collecting data that we didn't collect. Okay, so if someone else collected the data for us and gave us this data, most likely it contains these hidden confounders or these partially observable elements that are going to really bias our results. And we're not going to discuss this here. Here we're going to assume full observability, and we're going to talk about problems in which we don't assume this partial observable setting, but it's important to remember this. And again, I suggest everyone who is interested to go look at the tutorial by Elias Berenboim on this subject. So now that we're ready to talk about get into the details of offline reinforcement learning, let's try to understand why is it even hard. So let's start by looking at a very simple problem, a bandit problem, with one state. So we have a singleton state space. So we don't really care about the state. What we care about is choosing an optimal action, giving some kind of reward signal. Our reward is given by a function mu for every action plus normal noise. So that is our reward. And we're going to assume that data was collected for us by some unknown behavioral policy. And we get a data set of actions and rewards, these noisy rewards for every action. Now, what we're going to want to do is we want to find the optimal action, right? The action that would, in expectation, give us the optimal value, in this case, the largest mu. So how are we going to do this? One way we could do this is we could write a sample mean estimator for our mean, right? Mu hat. Then having this sample mean, instead of having an estimate for the means of every action, we could take a greedy policy, and the greedy policy would take the highest sample mean, the action that gives the highest sample mean, and that will be our policy. And just I'd like to note that these sample means are actually also normally distributed with mean, which is actually mu, they're unbiased, in a variance that goes like 1 over n. We'll see why this is important later on. And finally, I want to note that mu hat here plays the role of the Q function. If you recall earlier, we saw this general actor-critic framework where we first learn the Q function and then we try to be greedy with respect to this Q function, right? We try to maximize the policy with respect to this estimate of the Q function. So here we're doing the same thing, right? We're doing this actor-critic idea in a bandit setting, right? We're learning the mu hat here plays the role of q hat, of our q function. So we're trying to find a good approximation for mu, which is exactly our sample mean estimator, after which we take a greedy policy with respect to this mu hat, with respect to the q function. Okay, so this is our policy. Our policy is a greedy policy with respect to the sample mean estimator. Is this a good policy? This is what we would have done probably in an online setting. But here again, we have a fixed data set. We can't collect more data, so we're stuck with this policy. This is the final policy that we're going to output. Is this a good idea? Is this a good policy? Let's see what happens. Let's see what the suboptimality of this policy is. So the suboptimality is defined by the best policy, the reward of the best policy we could have taken, the expected reward, minus the expected reward of our policy, of our greedy policy. So this difference is equal to the difference between the expectation between the actual means. And if we add and subtract our estimator, our sample mean estimator, then we get two terms. Okay, and each term here has a significant meaning. The first term is actually a pretty simple term, right? It's the intrinsic uncertainty that we have in our estimator. The expectation is taken with respect to pi star. This is something that is defined by the environment. We can't control this. The only thing we can try to control to minimize this term is try to make mu hat as close as we can to the true mu for the optimal action, which we don't know. So the best thing that we could do is probably try to make mu hat as close to mu for every action. And this is really our sample mean estimator. So we know to try to minimize. So we have an idea how we can minimize this term. The more problematic term is the second term that we have here on the right. And this, we can call this term the spurious correlation term. And the reason is that we have an expectation over mu hat, but also the expectation is induced by a policy pi hat that was induced by our empirical estimator. So this becomes a little bit of a problem because pi hat was greedy with respect to mu hat. So what we're actually doing, this correlation term can become pretty large whenever mu hat is a bad approximation of the true mu, right? Let's see this graphically, why this would happen. So recall that mu hat is distributed normally with variance that goes like 1 over the number of times we sampled an action. So if we have an action that was sampled very little, then this normal distribution would be very wide, would get a very wide Gaussian distribution, meaning that if we have a lot of actions that were not sampled enough, then with a high probability, we'll have at least one action that will give us a large error for its mu, for its empirical mu estimator, right? And this would mean that we'd have a large error in mu hat minus mu, this second term that we saw earlier. What would happen then, that what we're actually doing, since we're greedy and taking the maximum mu hat, right? We're taking the action that would give us the maximum empirical mean. Then what we're actually doing is, in very high probability, trying to take an action that gives us a very large error. So we're actually being over optimistic here. And since we can't collect new data and we're only stuck with this finite data set that we originally got, being over optimistic, we're actually fitting ourselves to the noise in the data, to things that were not sampled enough. And this is problematic. This means that being over optimistic or being optimistic and greedy in an offline setup can be problematic in cases where we can't collect new data, right? So we're actually fitting to this noise. So in general MDPs, we would have a similar problem. Let's say we have some kind of estimator for our value and our Q function, which of course would be related. We create an estimated greedy policy pi hat, and let's denote by iota our Bellman error. So it's the Bellman operator applied on the value, estimated value, minus our estimated Q function. We want this to be as small as possible. And it can be shown that the suboptimality of pi hat can be separated into 3 terms. And here we still have these terms that we saw before in the bandit example. The first term is the problematic term. This is the term that is going to fit to the noise in the data. It's exactly the expectation over the Bellman error induced by our policy pi hat. And again, if the policy pi hat is greedy with respect to Q hat, then iota here, which the expectation is taking over, is defined by Q hat. So we have this spurious correlation, which can cause this term to be very, very large. This is the problematic term that we're going to try to make as small as possible. This is the term that is going to be large whenever we're too optimistic with respect to our estimated Q function. The second term, again, is the intrinsic uncertainty. This is the term that we can try to minimize. The expectation is over pi star, something that is defined by the environment. And we also get a third term here, which is the optimization error. Okay, so what can we do? We can add pessimism. How are we going to add pessimism? So let's say we have some kind of estimate for the Bellman operator. Okay, recall that the Bellman operator is the reward plus gamma, the expected value of the next state. Okay, so we have some way to approximate the Bellman function, maybe through data, right? We collect the data and we can take and we could use that to estimate the Bellman operator. And let's assume that for some reason we know we can bound the error between applying the approximated Bellman operator on the value, on our estimated value, and the true Bellman operator. And let's say we have some kind of bound, so we'll call this some kind of uncertainty oracle over this difference. If we have this, right, then we could write a different estimator for the Q function. Usually the estimator for a Q function would be just applying this Bellman operator over the estimated value function. But here we're going to subtract. We're going to be pessimistic. We're going to say, no, the true Q function can't be this large. We're going to subtract this U that we have, this bound that we have over the error on our Bellman operator. And if we do this, then one thing that we can notice is that minus iota, which was the spurious correlation term, which is equal to Q hat minus the Bellman operator over the value, we could write our Q hat, which is the Bellman operator over the value with the minus U, and we know that the first difference here is less than or equal to U, and therefore this whole term is less than or equal to 0. So using this bound and this estimator that was pessimistic, we are able to ensure that the spurious correlation term, which was the term that was problematic for us, is actually less than 0. We can bound our error. So this is good, right? So this is something good. So pessimism is something that would work for offline RL. And let's see this in an algorithm, in a value iteration algorithm. So the difference here between this and a regular value iteration algorithm is that we're going to add pessimism to our estimator. So we have some data set of states, actions, and rewards. The first thing we're going to do is given we have a current estimate for a value, we're going to apply the Bellman operator, our estimated Bellman operator, and subtract our bound over this estimate. Remember the bound that we saw before? That would be our and our estimator for the Q function would be some truncation. Here we're assuming we're truncating the Q function because we're assuming the reward is bounded between 0 and 1, so we can also bound. So we get a pessimistic estimator for the Q function. Then we could take the policy that would take the argmax, the best action, over this estimate of the Q function. Again, estimate our value using this Q function and go back and now create a new estimator for the Q function, which will be again pessimistic with respect to this new value. And we'll do this until we converge. Now, normally in regular value iteration without pessimism, if we have the full model and we have all the data in the world, we don't need it, right? We can run over all the states and actions and rewards. Then in regular value iteration, we would converge to the optimal policy. Here, since we're taking a pessimistic estimator, we have a suboptimality, which is bounded by this uncertainty term, our pessimistic uncertainty term in our error. All right, great. So we see that pessimism works for offline RL. We had this spurious correlation term, right, that made us over-optimistic, made our errors in the Q values be too large. And by adding or subtracting our bound on the error, right, on some error that we have on the Bellman operator, we were able to, by adding this pessimism, bound our error. Okay, and get better results. So this is a recurring method in offline reinforcement learning to in some way add pessimism in order to be able to solve the problem better. Okay, so pessimism is one thing. What other challenges do we have in offline reinforcement learning? So let's talk about some more practical challenges that we really have. These are both theoretical and practical. But recall that in offline reinforcement learning, we're giving a fixed data set. But actually, even if we were given an infinite data set, there's no reason to believe that we see the whole state space, right? Even if our data set is very, very large, because the policy in the data set, that generated the data set, might take certain actions in certain times and might never take different actions, might never bring us to states that we might want to learn about, right? So a very important challenge in offline reinforcement learning is generalization between states. How can we generalize to states that we don't have in our data set and we never will have in our data sets? So this is a problem that even occurs when our data set becomes very, very large. So another challenge that we might have is estimating uncertainty for offline RL. Why would we need to estimate uncertainty? So we already saw for our pessimism, we had to bound this error in our Bellman operator. Where do we get such a bound? Right? Sometimes you will see further on that estimating uncertainty means being able to know where we know a good model of the world, or where we are certain about the Q function of the world. And uncertainty estimation becomes the problem of offline RL in these settings, in these scenarios, right? The whole problem of offline RL reduces to being able to estimate uncertainty. This is also related to out-of-distribution detection, and this is a very hard problem. It's still an open challenge, an open problem in even of the field of supervised learning. Out-of-distribution detection becomes very hard in high dimensions. What other problems do we have? We have the problem of narrow distributions. Like I said earlier, this policy that generated the data might have a very narrow distribution, only taking very certain actions or being very deterministic and looking only at certain states. And the question there is how can we use such a policy to generate maybe a more expressive policy or something that we don't see in the data. Another problem with offline RL, another problem that we have is that offline data, unlike the imitation learning scenario, offline data might have very suboptimal examples in it. I mean, we might also have expert data, but this data might be very noisy with suboptimal examples. And many methods attempt to try to imitate the data while also learning a better policy or trying to be close in some manner to the behavior policy of the data. But if this behavior policy is pretty bad, maybe it's random, then being similar to the policy in the data or to the suboptimal examples might be very bad. So we want to try to find methods that are able to use the data while not being while not trying to be similar to the suboptimal parts of the data. So partial observability is also a very big problem. We've already touched it a little bit. Again, there's a great tutorial on on reinforcement learning and causal inference. And like I said earlier, when we deal with partial observability in offline RL or off-policy evaluation, we're actually talking about the problem of confoundness in causal inference, of hidden confounding. And this is a very big problem. In many cases, it's unsolvable. The problems are not identifiable. And then we need to bound this confoundness that we have in our data in order to reduce biases when we go to the real world. So this is a very real problem that is very real in real data sets. And it's important to remember that partial observability is present, and when dealing with offline reinforcement learning, many times the problems become unsolvable in a sense that even with an infinite amount of data, and even with a policy that is completely random and able to see all the actions and all the states, if we have something that we don't see in the data, then the problem might be not identifiable, unsolvable in a sense. We won't be able to converge to an optimal solution of the optimal policy. Other problems in offline RL include continuous time that we have in our data. We're not seeing the data in fixed time steps. Other than that, non-stationarity. Human beings are non-stationary by nature, and there's no reason to believe that our data was generated by a stationary policy. And there are many more problems. But now, in the next part of this tutorial, I want to talk about some practical algorithms for solving offline RL, and we'll begin by talking about two general methods for dealing with offline reinforcement learning: proximity and uncertainty. So two methods that we have for current offline reinforcement learning algorithms are methods that are based on proximity and methods that are based on uncertainty. Methods that are based on proximity try to to keep some sort of similarity to the data distribution, meaning we have some behavioral policy that generated the data, and we want to remain close to that behavioral policy. We don't want to take actions that are too different from this behavioral policy. This would help us control overestimation, as we'll only look at actions that we have enough in the data. Other methods are based on uncertainty. Uncertainty-based methods don't necessarily ask us to remain close to the policy distribution in the data, but rather only stay far away from areas of high uncertainty. So we get some conservative bounds of this level of uncertainty in our Q function or in our model, and we try to stay away from areas of high uncertainty. How do we measure such uncertainty? So this becomes a pretty hard problem, and the problem actually reduces to being able to measure this uncertainty. So let's see some examples of algorithms that use proximity and algorithms that use uncertainty. One example of a proximity-based method is batch-constrained deep Q-learning. And basically this algorithm works as the general actor-critic algorithm that we saw earlier, only it maintains closeness in distribution to the policy and the data, to the behavioral policy. So the first step would be to, using the data, train some kind of generative model of the behavioral policy in the data. So this could be a variational autoencoder, which basically maximizes the likelihood of the actions in the data and learns, tries to mimic the behavioral policy in the data. So now we have a generative model for the behavioral policy. Having this behavioral policy, we can sample a batch of states, action, rewards, and next states, sample actions from this behavioral policy, and perturb them. So we want to act like the behavioral policy, but we allow some perturbation around the behavioral policy. And now we're going to update our Q function like we would have updated it in the general actor-critic framework. Only now we're only going to take the maximum, right, our targets are gonna take the maximum over actions that were sampled by this perturbed version of the behavioral policy, over this approximated behavior policy. And this would allow us to still find a greedy policy with respect to the Q function, only we only allow it to be greedy with respect to actions that are still close to the behavioral policy. And this adds pessimism in a way that maintains similarity to the data distribution, and by that doesn't allow us to be too greedy to areas where we don't have enough data, to actions that we don't have enough samples from. So we're staying close to the behavioral policy in the data. After this, we can update our perturbation. Again, this perturbation, we don't allow it to be whatever we want, but we could update our perturbation function to be greedy with respect to that, and then still find a better policy than the behavioral policy in the data under this limit of being close to the actual policy in the data. So this is one thing that we can do. The problem with this is that being close to, in distribution, to the behavioral policy in the data would mean that if this behavioral policy was really bad, for example, if it was random, then we're actually doing something that is not so good, right? Because if the policy was completely random, and even if we had an infinite amount of data with the completely random policy that collected enough data of all the actions and all the states, then in that scenario, there's no reason to be similar to the behavioral policy in the data. In fact, we could run a regular Q-learning algorithm and find an optimal policy. So this is an algorithm that in a way is too pessimistic, or in a way too constrained to the distribution of the policy in the data. One way to improve this idea is by, instead of being close in distribution to the behavioral policy, try to only match the support of the behavior policy. Because remember, one of the problems that we saw is that the fact that we have a small number of action samples makes us be over-optimistic. So if we only match the distribution of the data in its support, then we might get better results. And indeed, bootstrapping error accumulation reduction, the algorithm BEAR, this is what it does. Instead of matching the distribution of the behavioral policy and data, it only matches the support. And it uses maximum mean discrepancy to do this. So it uses basically the same framework, only this is the way it constrains the policy to the data. Other ways to be pessimistic and constrain the policy is by penalizing the Q function, the critic. Instead of directly penalizing the policy, we can penalize the Q function. So if we look at the TD error, right, which is R plus gamma, the expected value of the next state, minus our Q function, then we want to find the Q function that would minimize this TD error. And this is what we would do in both general actor critic and Q-learning. We would minimize this error. And when you saw that this is not a good thing to do in offline reinforcement learning, because it makes us be too optimistic. So one thing that we can do, we could add pessimism by regularizing the Q function in this term, right? So our template would be to, instead of minimizing J of Q here, the TD error, we would minimize a regularized version of this function. So let's see some examples of such regularizers. One algorithm, AlgaDice, actually looks at a dual formulation of the problem, but eventually finds an actor-critic type algorithm which minimizes this type of function with a regularizer that is equal to the expectation over the Q function. Meaning we're trying to minimize the TD error plus a regularizer that won't let the Q function of our policy be too large. That's one regularizer we could use. Another form of regularizer, or there's a family of regularizers here that we could use, is adding a discrepancy between the behavioral policy and our policy in terms of maximum entropy. And it's known that the maximum entropy policy can be written in terms of the Q function as the exponent of the Q function over the integral over all the actions. And that is actually our policy in terms of the Q function. So implicitly, by minimizing, adding a regularizes, which minimizes the distance between the behavioral policy and our policy in terms of the Q function, we're actually regularizing the Q function implicitly. Now, if this discrepancy is the KL divergence, then we get one of the variants of conservative Q learning. When this distance is the Fisher divergence, we get Fisher behavior regularized critic. So there are many different algorithms that we could form using this distance, this regularizer. Now we talked about methods to penalize the policy through proximity. We talked about ways of adding a penalty to the critic, to the Q function, in order to make it not be too optimistic. Let's talk about uncertainty now. How can we add uncertainty? Now, one way to add uncertainty is to add uncertainty in a model-based framework. So a model-based framework and model-based offline reinforcement learning would first try to construct a model of the environments, right? So we have data, we can maximize the likelihood, and we could form a model of the environment. So we have this p hat of the environment. And then from assuming that we can achieve some kind of uncertainty metric over our model, meaning bound the error between our approximate model and the true model of the world, then we could try and solve a different MDP, a pessimistic MDP, in which whenever we reach states in which our uncertainty is too high, then we would give the agent a negative reward of negative kappa and also terminate the episode. So that's one way to incorporate this pessimism through uncertainty. So whenever our uncertainty is too high, meaning whenever we are unsure about our model, we would terminate the episode and give a negative reward. Another way to do this is through an algorithm called MOPO. It basically does the same thing. It tries to construct a model of the world using our data, assumes we have some kind of uncertainty metric over our model, meaning some kind of measure of the error bound over the error of our model. And having this, now what MOPO does is, instead of terminating the episode and giving a negative reward, in each stated action, it simply subtracts the amount of uncertainty it has on the model. And this basically gives the same result. Right, so, but one of the problems is how do we estimate this uncertainty, right? I told you we're assuming we have this uncertainty oracle that is able to give us a bound over how far we are from the true model. And essentially, the whole problem of offline RL, once we've created our new MDP, reduces to being able to estimate uncertainty, because solving online RL algorithms is something that we know how to do pretty well already. So once we have this approximate simulated MDP and this uncertainty oracle, we know how to solve online RL algorithms great, right? So the problem reduces to being able to estimate this uncertainty. How can we estimate it? So we could use confidence sets like UCB, LCB, ensemble methods, Monte Carlo dropout. We could model the distribution over the functions. For example, in variational autoencoders, the variance of the output could measure our uncertainty, and there are many more ways. And this is a hard problem and an open question of how to measure uncertainty. But once we're able to do this, we can stay far away or give a negative reward whenever we're too close to areas of high uncertainty. Now that we have seen a couple of recent algorithms for solving offline RL problems, we're left with the question of how to evaluate our algorithm. So there are currently two central data sets for evaluating offline RL algorithms. The first is D4RL, datasets for RL, and mostly contains continuous control tasks, but also tasks with varying quality of data sets. So we have data sets with completely random agents, data sets with mediocre agents, and data sets with expert agents or mixed agents that are partly good at certain states and bad at different states. And this allows us to really test our algorithms in many different quality of data sets. Other than that, we also have RL Unplugged. It also contains games from Atari Suit, continuous control tasks, and they also explore various challenges of offline reinforcement learning. I'm hoping to see more and more data sets come out with more problems, including problems of partial observability and all the different challenges that we talked about earlier. Finally, I'd like to talk about the problem of choosing our method of evaluating or validating our offline RL algorithm. So one way to do this, one way to validate our algorithm is go to the real world, right? Go to the real environment and actually test our policy. The problem is that this is not very realistic to do. In many different domains, this would actually be impossible. Maybe only at test time, after we're pretty sure that our policy is good, we could do this. Also, this might cause some biases if we in the research community create algorithms that are based on evaluation in the real world. Then whenever we won't be able to do such a thing, then we might not be able to find the proper fit for our algorithms. So we might want to find methods for evaluating or validating our algorithms in an offline manner, using our offline data. One way to do this is using off-policy evaluation. And I remind you that off-policy evaluation is the process of finding the value of a given policy using the data that was generated by the behavioral policy. The problem is that off-policy evaluation algorithms currently don't really scale that well. And even if we did have a perfect or a very good off-policy evaluation algorithm, it would always have some kind of error, right? So this would cause this imperfect selection of an algorithm. Unlike in supervised learning, for example, when we try to validate, we have this ground truth of labels. Here, we would have noisy labels of what would be a good policy, which would make it harder for us to fit our model or do this hyperparameter tuning. Other questions that we could ask is, what data should we use? For off-policy evaluation, we need a large amount of data. Should we take a large portion of the data and evaluate our policy on that? What off-policy evaluation algorithms should we use? There are many different kinds. And how do we tune this off-policy evaluation algorithm together with our offline RL algorithm? We have hyperparameters here, we have hyperparameters there. How do we tune both of them together? These are all really hard and open questions that we should ask ourselves in order to be able to validate our offline RL algorithms offline. So thank you for joining my tutorial. There are many more open challenges in offline reinforcement learning, as we discussed earlier. One of the most major problems is the problem of partial observability, which relates to the problem of causal inference. As we discussed earlier, there are still a lot of challenges, a lot of work to do, and I believe we will be seeing a lot of really interesting work in the near future.